In this video, I will attempt to walk you through my new and improved Angry Bird launcher, which now, instead of just flying through the air and never stopping, actually hits the pyramid and rolls somewhat down the hill in this case. So to do this, the first essential step is figuring out the path of the Angry Bird. And you can see I have already figured it out because I've plotted it here. And if I move the bird, you can see that that path changes. Now you have been getting this path through parametric equations, and you have been able to trace the path, but you haven't actually created an equation which is the path as a function. And if we can find that function, then we can simply do an intersection with this line, and that is point E. And that is simply done by clicking on or constructing the intersection of the two objects like that. So, like I said, the first goal will be finding the equation for the path of the object. So to do that, I'm going to take my parametric equations for the projectile path and eliminate t. Here are our projectile motion equations that we have worked with. The only addition is that now we can see the starting point, x sub 0 and y sub 0. So here are all of the definitions of the parts of these equations. So we start at x sub 0, y sub 0. V is the velocity. In this case, I have that represented by the distance of the slingshot is moved back times a constant called VEL in my sketch. Theta is the launch angle, and time is what's actually varying, and time will determine the location, which is x comma y. So what I want is an equation for y that is in terms of x, so a function for the path of the bird, not a parametric pair of equations, which basically means I need to eliminate t, get rid of t in these equations. To do this, I will solve for t in the first equation, and then substitute its expression into t of the second equation. So in the first equation, if I isolate t, I get that x minus x sub 0 equals v cosine theta all times t. Therefore, t equals x minus x sub 0 over v cosine theta. So now I'll take this expression and I'll plug it in to every instance of t in the second equation. So this is what I'll end up getting. It looks complicated, but it looks more complicated than it really is due to all of the different constants. When I enter this into Sketchpad, you'll be able to click on the velocities and the angles and so forth to create this equation. It does simplify somewhat if you notice that this v will cancel with this v, and sine divided by cosine is tangent. So I end up with this equation, which I will take over to Sketchpad. And so here is the equation that you just saw on the previous screen, but using the constants that I've already measured up here. And if you graph this, it should give you a parabola, and then if you launch your bird should follow the exact path of the parabola. The next step would be to click on the to create a line, you probably don't have this line yet, CD, by just eyeballing the tower, and then click on the intersection to create point E. So in the first part of this video, I shared with you how I generated the equation, or the function, of the path of the bird. And you can see it down here. This is that function. So I've graphed it, and I can see where it intersects this blue line. And the blue line is actually, has just been placed to coincide with the side of this tower. If my picture were firmly in place, I could maybe have plotted the points D and C so they would be fixed. As it is, this is fine for this context. So I have clicked on the intersection of these two graphs, and I've gotten point E. So now I will measure the X and the Y coordinates of point E to use them in my calculations. I'll bring those over here. And actually I'll take a screenshot and then take them over to my calculation page where I was working. Okay, we're back here on my calculations, and I have just found that the point of intersection is point E, and here are the coordinates. So here's my point, and my next goal is to find how long it will take for the bird to get to that point. I have an equation which is over here, which tells me how long it takes to get to any point. Having solved for t, this equation will tell me how long it takes to get from my initial point, which is x sub 0, to any other point. So if I put in x sub e into that equation, I'll get x sub e minus my initial x value divided by v times the cosine of theta equals t. So now I'll type that into Sketchpad. This is where I have inputted into Sketchpad the x-coordinate of e minus the x-coordinate of my initial point divided by the velocity times the cosine of the angle. So right now it will take 1.89 seconds to get to point E. And because this is dynamic, if I change the original location of the bird, the time will change also, because E changes and therefore the time. So this is getting a little bit messy. I'm going to now change the label here to read time to E. Here are the projectile path equations that I used and you used from the very beginning. So now I want to restrict this so that it only graphs for the time from 0 to, right now, 1.45 seconds, or in general, this calculation time to E. So I will double click on either one of these, and I will divide it by the square root of the signum of that value minus the time. And that will restrict it to be only graphed for the values of t that are less than 1.45. Let's test it out. So now if I launch, okay, he starts to do a different path, and that is an extension of this. But right now we have succeeded in making him stop when he hits the wall, which was the main goal.